The universe began in absolute darkness. Then the first photon sparked. This single event set the stage for all of existence, and its story is written in the light that fills our cosmos. By the end of this journey, you will see the night sky not as random points of light, but as a living history book written in photons. We will trace light's path from the fiery birth of the cosmos to the deep cosmic echoes that still whisper to us today. How did these ancient rays sculpt the galaxies and stars we see? What secrets about our ultimate fate are carried in their glow? What does it mean that we are made from starlight that has traveled for billions of years to reach us? For nearly 400,000 years, the universe remained a searing fog. Light could not travel freely, as each newborn photon was immediately captured and scattered by a chaotic sea of charged particles. It was a brilliant prison, a cosmos filled with light that could not see its own hand in front of its face. Then, in a pivotal moment known as recombination, the expanding cosmos finally cooled enough for a fundamental shift. Electrons slowed their frantic dance and were captured by protons, forming the very first neutral atoms. In that instant, the prison walls came down. The photons, once perpetually trapped, were suddenly set free. They burst forth in every direction, and the universe became transparent for the very first time. That first flash of liberated light is still with us today. We call it the cosmic microwave background, and it is the oldest picture we have of everything. The physicist George Smoot famously called it the afterglow of creation, and it is a perfect description. This radiation is a fossil, a snapshot of the infant universe imprinted onto the fabric of space itself. By studying its faint whisper, we can read the story of that primordial dawn. The temperature and density of that early cosmos are written into the subtle patterns within this light. These minute fluctuations, these tiny wrinkles in spacetime, were the seeds of everything to come. They were the gravitational blueprints for all future cosmic structures, the slight over densities that would one day collapse to form galaxies, stars, and planets. Every single photon from that event carries a piece of that original information. Its journey began at the moment of liberation, and it has been traveling for over 13 billion years to reach our telescopes. What stories could it tell if we could listen closely enough? This ancient light is not just a relic. It is a living message, a constant reminder that the universe was once small, hot, and incredibly uniform. Yet, encoded within that uniformity were the slight imperfections that gave rise to the magnificent complexity we see today. It is the ultimate origin story, written in light and delivered across the ages. That first light did not simply fill the empty cosmos. It began to build it. Think of light not as a passive glow, but as a cosmic sculptor, a fundamental force that carved the structures we see in the night sky. After the cosmic background radiation faded into the darkness, the universe entered its formative years, a time known as the cosmic dark ages. For millions of years, there were no stars, no galaxies, only vast, silent clouds of pristine hydrogen and helium gas. Then, gravity began to pull on the tiny wrinkles left in the cosmic microwave background, gathering these immense gas clouds into the first proto-galaxies. Deep within these cosmic nurseries, the very first stars ignited. They were not like our sun. These first stars were behemoths, hundreds of times more massive, and they burned with a ferocious, short-lived intensity. Their light was a new kind of power in the universe, a brilliant, destructive, and creative force. The ultraviolet radiation pouring from these stellar giants was so energetic it ripped electrons away from the neutral hydrogen atoms that filled space. reionizing the cosmos in a great wave of transformation. This process, called cosmic reionization, cleared the fog once and for all, making the universe permanently transparent to light and shaping the distribution of matter on the largest scales. This light exerted a physical pressure, literally pushing on the gas and dust around it. In stellar nurseries like the Orion Nebula, we see this cosmic feedback in action today. The intense ultraviolet light from brilliant newborn stars boils away the very gas cloud that gave them birth, sculpting vast pillars of dust and halting the birth of new stars in their immediate vicinity. This is photoevaporation, where light acts as both creator and destroyer. It forges stars and then it disperses the raw materials, regulating the pace of star formation across a galaxy. Light revealed another, more mysterious architect at work. When astronomer Vera Rubin studied the rotation of galaxies, she found something perplexing. The stars at the outer edges of galaxies were moving far too quickly. According to the laws of gravity, these galaxies should have flown apart. The only explanation was that they were held together by the gravitational pull of something invisible, a substance we now call dark matter. It was the light from those stars, analyzed through its spectral fingerprints, that told us this hidden cosmic scaffold exists, guiding the formation of galaxies from the shadows. Every color and every line in a star's spectrum is a message, a precise story of that star's composition, temperature, and motion. So how do we learn to read this ancient language written in light itself? A brilliant rainbow holds the universe's deepest secrets. That simple band of color, when stretched and examined, becomes a cosmic barcode, and the story of its decoding begins with a glassmaker's puzzling discovery. In the early 1800s, a German scientist named Joseph von Fraunhofer was perfecting his lenses when he noticed something strange. By passing sunlight through a narrow slit and then a prism, he saw that the beautiful spectrum was not a smooth, unbroken gradient of color. It was scarred by hundreds of fine, dark lines like cracks in a stained glass window. He meticulously mapped these lines, but he had no idea what they were. They were, in fact, the chemical signatures of the sun itself. This was the moment spectroscopy was born, the art of reading light to understand the substance of the stars. Every element in the universe leaves its own unique mark on light. When a star's intense, hot interior produces a continuous spectrum of color, that light must pass through the star's cooler outer atmosphere. Atoms in this gaseous layer act like selective sponges, absorbing very specific wavelengths of light that correspond to the energy needed to bounce their electrons into higher orbits. The missing wavelengths appear as dark lines in the spectrum we observe. These are absorption lines, and they are the element's fingerprint. A set of lines in a specific pattern reveals the presence of hydrogen. Another distinct set points to iron or calcium. It is a direct chemical analysis performed across the vast emptiness of space. This principle is governed by what we now call Kirchhoff's laws of spectroscopy. They tell us that a hot, dense object like a star's core produces a continuous rainbow of light. A hot, diffuse gas, like a neon sign or a distant nebula, will glow with its own bright emission lines. And a continuous light source passing through a cooler gas gives us the dark absorption lines that Fraunhofer saw. With these rules, a spectrum becomes a detailed cosmic report card. The overall color tells us the star's temperature. A blue star is fiercely hot, while a red star is relatively cool. The specific patterns of lines reveal its exact chemical composition. We learned that the sun contains sodium, magnesium, and silicon, all identified from 93 million miles away. But the story written in light did not stop with ingredients and temperatures. Early in the 20th century, astronomers noticed that the spectral lines from most distant galaxies were not in their expected places. They were systematically shifted toward the red end of the spectrum. This redshift was a monumental clue. It worked like the changing pitch of a siren on a passing ambulance. As the ambulance moves away from you, the sound waves are stretched, lowering the pitch. In the same way, as a galaxy moves away from us, the light waves are stretched, shifting its spectral fingerprint toward red. Edwin Hubble connected this redshift to distance, realizing that the farther away a galaxy was, the faster it was receding. The light itself was delivering the most startling news of all. The entire universe is expanding. So what other secrets are hidden in this ancient code? The extreme redshift of quasars tells us they are the impossibly bright, incredibly distant hearts of young galaxies, powered by supermassive black holes. The specific light curves of a supernova's explosion reveal not only the star's death throes but also serve as a standard candle to measure vast cosmic distances. Every photon is a messenger, and we have only just learned its language. To catch more of these faint whispers from the edge of time, we had to build greater eyes, instruments that could gather light beyond the limits of our own. Galileo's first telescope was little more than a tube with two lenses, yet it shattered the celestial sphere. When he pointed it at Jupiter in 1609 and saw 4 tiny moons orbiting the giant planet, he proved that not everything revolved around the Earth. This was the first crack in an ancient worldview, a demonstration that light, when gathered and focused, could reveal truths that defied common sense. That simple instrument began a revolution, an unbroken chain of innovation dedicated to catching more light. Each leap in technology peeled back another layer of the cosmic onion. Refracting telescopes with their glass lenses gave way to immense reflectors that used mirrors to capture fainter glows from deeper space. Then we learned to see in colors invisible to our eyes. Radio telescopes, like giant satellite dishes, tuned into the long-wave whispers of the cosmos, including the faint static of the cosmic microwave background, that primordial echo from the beginning of time. Infrared telescopes peered through obscuring clouds of dust to witness the birth of stars hidden within. But our atmosphere remained a shimmering barrier, blurring the finest details. The solution was to rise above it. The Hubble Space Telescope, launched into Earth's orbit, became our first great eye in the vacuum of space. Free from atmospheric turbulence, its crystal-clear vision transformed our understanding. Astronomer Nancy Grace Roman, a driving force behind Hubble, championed its ability to see in ultraviolet light. This allowed Hubble to precisely date the formation of galaxies, tracing their evolution by analyzing the specific light from their youngest, hottest stars. Its most profound achievement might be the Hubble Deep Field Image. By staring at what seemed like an empty patch of sky for days, it gathered ancient photons that had traveled for billions of years. The result was not darkness, but a universe teeming with thousands of galaxies, each a smudge of light representing an entire island of stars. That single image captured the immense depth of cosmic history, all contained within a speck of sky the size of a grain of sand held at arm's length. This telescopic journey is far from over. The James Webb Space Telescope, with its giant gold-plated mirrors tuned to the infrared, is designed to see even further back in time, to an era when the very first stars and galaxies were beginning to ignite. With every larger, more sensitive instrument we build, we gather more of these ancient photons, these faithful messengers, and they are now telling us a story that defies all expectation, pointing toward a force that is ripping the very fabric of the cosmos apart. The universe was supposed to be slowing down. For decades, the prevailing wisdom held that the mutual gravitational pull of all the matter in the cosmos was acting like a cosmic brake, gradually decelerating the expansion that began with the Big Bang. Then, in the late 1990s, two independent teams of astronomers made a discovery so shocking it would later earn them a Nobel Prize. They were observing a special kind of stellar explosion, a Type Ia supernova, in incredibly distant galaxies. These supernovae are cosmic mile markers because they all explode with nearly the same intrinsic brightness. They are known as standard candles. By measuring how bright they appear to us, astronomers can calculate their true distance with remarkable precision. Saul Perlmutter, Adam Rees, and their colleagues found that these distant supernovae were significantly dimmer than they should have been. The only possible explanation was that they were much farther away than anyone had predicted. The expansion of the universe was not slowing down, it was speeding up. Something was forcefully pushing galaxies apart, a mysterious something we now call dark energy. This discovery turned cosmology on its head. The light from these dying stars, traveling for billions of years, carried a message we did not expect to receive. It told us that the cosmos is dominated by a repulsive force, an energy inherent to the fabric of space itself. To understand its nature, physicists describe it with an equation of state, a single number that represents the pressure this energy exerts. If this number is exactly -1, it suggests dark energy is a constant property of the vacuum of space, a concept Albert Einstein once called his greatest blunder, the cosmological constant. This has profound implications for the ultimate fate of everything. In this scenario, the acceleration continues forever. Galaxies will be pushed apart until they are isolated islands, their stars will burn out, and the cosmos will slowly fade into a cold, dark, and empty state, a final big freeze. Projects like the Dark Energy Survey are now mapping millions of galaxies to measure the strength of this force throughout cosmic history, trying to pin down its true nature. But what does this mean for light itself? In an eternally accelerating universe, the light from most galaxies will one day stretch so far into the infrared that it will become undetectable, and eventually the cosmic horizon will shrink, leaving a future civilization with a sky that is mostly black. The very photons that carry our history are racing into a future shaped by this invisible hand. Yet light has one more trick to play, a way to reveal the invisible cosmic scaffolding that dark energy pushes against. It does not always travel in a straight line. Light itself can bend, curving around the colossal weight of galaxies. This is not science fiction, but a direct prediction of Einstein's theory of general relativity. Einstein proposed that massive objects do not simply sit in space, they warp the very fabric of spacetime around them. Think of spacetime as a taut, flexible rubber sheet. Place a heavy bowling ball in the center, and it creates a deep dimple. Now roll a tiny marble past the edge of that dimple. The marble's straight path will curve following the contour of the dent. Light behaves exactly like that marble. It travels the straightest possible path through a curved universe. So when light from a brilliantly distant object, like a quasar, passes near a massive galaxy cluster, its path is bent. From our viewpoint, the quasar appears in a slightly different position in the sky. In extreme cases, this creates multiple images of the same single object, or even a perfect circle of distorted light known as an Einstein ring. It is a cosmic mirage, proving that space itself is malleable. Astronomers classify this phenomenon into three powerful tools. Strong gravitational lensing creates those dramatic multiple images and rings, effectively turning a galaxy cluster into a natural telescope. The Hubble Space Telescope's Frontier Fields program used this very technique, leveraging the gravity of massive clusters to magnify the faint light of galaxies from the universe's first billion years, galaxies we would otherwise never see. Then there is weak lensing, a more subtle effect. The light from entire fields of distant galaxies is ever so slightly stretched and distorted as it passes through the diffuse halos of dark matter surrounding foreground clusters. By meticulously measuring these tiny distortions, we can literally map the invisible cosmic scaffolding of dark matter. As physicist Kip Thorne has explained, gravitational lensing provides one of the most stringent tests of general relativity and our most direct way to weigh the unseen mass of the universe. Finally, there is microlensing, where a single star or planet momentarily focuses the light of a background star, causing a brief, telltale brightening. This method has even been used to discover rogue exoplanets, worlds drifting alone in the dark between stars. Every bent beam of light is a messenger, revealing the hidden architecture of the cosmos. It allows us to see the unseeable, to trace the outline of dark matter with the only tool that can touch it, light itself. But the oldest light of all carries an echo from a time before stars or galaxies even existed. That faint hiss in their radio telescope was a mystery Arno Penzias and Robert Wilson could not explain. It was 1964, and the two radio astronomers at Bell Labs were troubleshooting their sensitive new instrument, plagued by a persistent, uniform static that came from every direction in the sky. They scrubbed the giant horn antenna, even evicting a pair of pigeons and cleaning up their droppings, but the annoying signal remained. They had, completely by accident, stumbled upon the oldest light in the universe. This was not mere static. It was the cosmic microwave background, the cooled and stretched remnant of the universe's fiery birth, the very afterglow of creation itself. That universal glow had been predicted by the Big Bang theory, and its discovery was the final, definitive proof that our universe had a specific, hot beginning. The entire cosmos is bathed in this fossil light, which has cooled over 13.8 billion years to just a few degrees above absolute zero. But this ancient glow is not perfectly smooth. Think of it as the surface of a quiet pond, its subtle ripples telling a story of the winds that passed over it long ago. Embedded within the cosmic microwave background are tiny temperature fluctuations, minute variations in the heat of the early universe. These anisotropies, as scientists call them, are the cosmic blueprints for everything. They are the seeds of gravity, the slightly denser regions where matter began to clump together, eventually collapsing under their own weight to form the vast cosmic web of galaxies and galaxy clusters we see today. To read this ancient text, we sent sophisticated missions into space. The COBE satellite first confirmed these tiny wrinkles in the fabric of the cosmos. Later, the WMAP and Planck missions mapped them with breathtaking precision, producing an all-sky map of the infant universe. These maps revealed the universe's shocking composition. We learned that the ordinary matter that makes up stars, planets, and us constitutes less than 5% of everything. The rest is the invisible pull of dark matter and the repulsive push of dark energy. The patterns in the light hold even deeper clues. One of the most important is something called Baryon acoustic oscillations. In the primordial plasma, gravity tried to pull matter inward, while the intense pressure of radiation pushed it outward. This created vast, spherical sound waves that rippled through the early cosmos, freezing in place the moment the universe became transparent. We see the fossilized imprint of these waves in the cosmic microwave background, a preferred spacing between galaxies that acts as a cosmic ruler, allowing us to measure the expansion history of the universe. Furthermore, the light's polarization, the specific direction its waves vibrate, carries the imprint of gravitational waves from the universe's first violent moments of inflation, a period of faster-than-light expansion. So what do these primordial whispers tell us? They confirm our universe burst from an incredibly hot, dense state. They reveal its exact age and composition. And they provide our strongest evidence for cosmic inflation, that spectacular growth spurt in the first fraction of a second that planted the seeds for all structure. This ancient afterglow is the ultimate origin story, but light also writes the final chapters, chronicling the spectacular deaths of the very stars it helped to create. A star's death throws forge the very elements of life. Deep within a massive star, a silent drama unfolds for millions of years. The star burns through its nuclear fuel, fusing lighter elements into heavier ones, layer by layer, like a cosmic onion. At its heart, an iron core grows, but iron is nuclear ash. It cannot be fused to release more energy. When that core becomes too heavy to support its own weight, it collapses catastrophically in less than a second. The outer layers of the star crash down and then rebound in a titanic shockwave, ripping the star apart in a core collapse supernova. For a few glorious weeks, this single dying star can outshine its entire host galaxy, flooding the cosmos with a light show of unimaginable power. The flood of light and neutrinos from supernova 1987A, which exploded in a nearby dwarf galaxy, provided a direct window into this violent process, confirming our models of stellar death. The light from such an event tells a detailed story. Its light curve, the precise way its brightness rises and falls over time, acts as a signature. For a specific type called a type Roman II supernova, this curve reveals the star's original size and the physics of its collapse. The spectrum of that light is even more revealing. In the blistering furnace of the explosion, elements are forged through rapid neutron capture, creating gold, silver, uranium, and other heavy atoms. The spectral lines we see are the direct fingerprints of this cosmic alchemy, a fresh batch of elements being blasted into the interstellar medium. We can see this legacy in the Crab Nebula, the glowing, tangled wreckage of a supernova recorded by Chinese astronomers in 1054. Its swirling filaments, illuminated by a pulsar at its heart, are rich with the newly synthesized elements that will one day be incorporated into new stars, planets, and perhaps even life. But there is an even more extreme cosmic finale. Occasionally, the universe unleashes a gamma-ray burst, the most powerful electromagnetic event known. For a few seconds, this narrow beam of energy can release more light than the sun will emit over its entire 10 billion-year lifetime. Many of these incredible flashes are thought to be the birth cries of black holes, generated during hypernova, the collapse of exceptionally massive stars, or from the violent merger of two neutron stars. The afterglow of such a merger, observed in both gravitational waves and light in 2017, confirmed that these collisions are indeed cosmic forges for the heaviest elements. The brilliant, fleeting light of a gamma-ray burst is a beacon across the cosmos, its rapid fade and afterglow spectrum allowing us to probe the most distant reaches of the universe and the conditions in young galaxies. These spectacular deaths are not an end but a scattering of seeds. The iron in your blood, the calcium in your bones, the oxygen you breathe, all were cooked in the heart of a long-dead star and dispersed across the galaxy in a final, glorious flash of light. We are quite literally the children of starlight, our very existence written into the universe by its most destructive and creative moments. This light carries the story of our own origins, but it also points toward an even grander cosmic structure, a web of invisible filaments that guides the flow of galaxies across the void. Every photon reaching us is a time traveler from a distant past. Its color tells a story not just of its origin, but of the epic journey it has taken through an expanding cosmos. When astronomers like Edwin Hubble analyzed the light from distant galaxies, they found a consistent and startling pattern. the familiar spectral fingerprints of elements like hydrogen and calcium were all systematically shifted toward the red end of the spectrum. This was not a change in the star itself, but a cosmic effect. The very fabric of space is stretching, and as light waves travel through this expanding medium, they are themselves stretched to longer, redder wavelengths. This is cosmological redshift, a direct measure of the universe's growth. Hubble's monumental realization was that the greater the redshift, the farther away the galaxy, and the faster it is receding from us. This single observation shattered the idea of a static universe and laid the foundation for the Big Bang theory. We are not at the center of a retreating cosmos, but rather, every point in space is moving away from every other point, like raisins in a rising loaf of bread. This is different from the more familiar Doppler effect, which shifts the light from a single moving object, like a speeding ambulance. Cosmological redshift is a cumulative effect, a stretching that happens to light over its entire multimillion-year voyage. This makes redshift a perfect cosmic clock. The galaxy known as GNZ11 holds the current record with a redshift of 11.1. This staggering number means we are seeing it not as it is today, but as it was a mere 400 million years after the Big Bang, a glimpse into the universe's infancy. Astronomers like Wendy Friedman have spent decades refining the measurement of the Hubble constant, the rate of this cosmic expansion. Using powerful telescopes like Keck, they observe the redshift of galaxies to calibrate this fundamental number, a key to understanding the universe's age and ultimate fate. So when you look at a faint red smudge in a deep field image, you are peering back through billions of years, witnessing a galaxy in its youth. That light has been traveling for almost the entire history of existence, a faithful messenger from an era long gone. But this ancient light does not travel through a perfect vacuum. On its incredible journey, it must pass through the vast, sparse clouds of the interstellar medium. Across the vast emptiness between stars, light does not travel alone. It navigates a complex obstacle course of gas and dust known as the interstellar medium. This is not a perfect vacuum, but a sparse haze of individual atoms, molecules, and tiny grains that fills the galaxy. When starlight encounters these microscopic obstacles, its journey is subtly altered. Tiny dust grains, smaller than a wavelength of visible light, are exceptionally effective at scattering blue light, much like our own atmosphere makes the sky appear blue. This means that as starlight passes through these cosmic clouds, the blue wavelengths are scattered away from our line of sight, leaving the light that finally reaches us noticeably redder. Astronomers call this interstellar reddening, and it is the reason a distant star that should appear white or blue often looks orange or red to our telescopes. This is different from cosmological redshift, which is caused by the expansion of space itself. Reddening is a local effect, a filter of dust that changes the star's apparent color. The dust can also block light entirely, a process called extinction, which creates those dramatic dark lanes we see slicing across the bright band of the Milky Way. These are not empty voids, but dense, cold clouds of gas and dust so thick they absorb the light from the stars behind them. The famous Horsehead Nebula is a perfect example, a dark silhouette of cosmic dust projected against a glowing pink background of ionized hydrogen. It is within these very dark nebulae, shielded from disruptive outside energy, that the cold gas can collapse under gravity to form new generations of stars. But the interstellar medium is not only a place of shadow, it is also a canvas for spectacular color. In regions like the Orion Nebula, the intense ultraviolet radiation from newborn, massively hot stars bombards the surrounding clouds of hydrogen gas. This powerful light rips electrons away from the atoms, ionizing the gas. When those electrons eventually recombine with protons, they release energy in the form of light, causing the entire cloud to glow with a characteristic reddish-pink hue. This is an emission nebula, a cosmic signpost pointing to a stellar nursery. The specific colors emitted are a direct result of the gas's chemical composition. The pioneering astrophysicist Cecilia Payne-Gaposchkin first deciphered this stellar language. Her work demonstrated that the spectral lines we observe are not just identifiers, they are precise measurements of abundance. She revealed that the strange, dark lines in the sun's spectrum were not caused by unknown elements, but by common ones like hydrogen and helium, just under unfamiliar conditions. Her analysis proved that hydrogen is the overwhelming constituent of stars, and by extension, the universe. This same principle applies to the glowing clouds of the interstellar medium. Each element sings its own specific color, and by listening to that spectral song, we can determine exactly what the cosmos is made of. But how does light, after running this cosmic gauntlet, reveal forces we cannot see? The answer lies not just in its color, but in its very vibration. As starlight passes through clouds of dust that are aligned by magnetic fields, the grains polarize the light, causing its waves to vibrate in a preferred direction. By measuring this subtle polarization, we can trace the invisible magnetic fields that weave through the galaxy, guiding the flow of gas and the birth of stars. That same glare you block with polarized sunglasses holds a key to the universe's invisible architecture. Sunlight bouncing off a lake becomes polarized, its light waves vibrating predominantly in one direction. Out in the cosmos, this same principle applies on a grand scale, but instead of water, the scattering is done by tiny, needle-like dust grains. These microscopic particles are not randomly tumbled. They are slowly spun and aligned by the gentle, pervasive pull of magnetic fields that weave through the emptiness of space. When starlight encounters this ordered army of dust, it too becomes polarized, its waves forced into a specific orientation. By measuring the direction of this vibration, we can trace the invisible magnetic field lines themselves. It is like seeing the wind by watching how it bends a field of wheat. This polarized light allows us to map the magnetic skeleton of our own galaxy, revealing vast, ordered fields that channel the flow of gas and influence where new stars can be born. But dust is not the only source of this cosmic polarization. A far more energetic process creates an even more distinct signal. When electrons, accelerated to nearly the speed of light, spiral around magnetic field lines, they emit a brilliant, focused light known as synchrotron radiation. This light is inherently and strongly polarized, a direct beacon pointing to the presence and structure of powerful magnetic fields. We see this in the Crab Nebula, the remnant of a supernova explosion. Its ghostly blue glow is highly polarized, painting a vivid picture of the intense magnetic fields that act as a natural particle accelerator, whipping electrons to incredible speeds. To quantify these subtle whispers of polarized light, astronomers use a set of measurements called Stokes parameters. These four numbers precisely describe the intensity and polarization state of light, allowing instruments like the polarimeter on the Planck spacecraft to create all-sky maps of magnetic fields, from the delicate structures in star-forming clouds to the vast halos surrounding entire galaxies. The most profound search, however, is for a specific pattern within the oldest light we can see. Researchers like John M. Kovac have hunted for a faint, curling signature in the cosmic microwave background known as B-mode polarization. This unique swirl is the predicted imprint of primordial gravitational waves, ripples in space-time itself generated during the universe's violent inflationary birth. Finding this pattern would be like hearing the echo of creation's first shudder, a direct glimpse into the universe's first moments. What secrets do these aligned photons hold? They reveal the force fields that sculpt gas clouds into stars and guide the evolution of galaxies. They are the silent cartographers of the cosmos, drawing maps of forces we can feel but not see. This dance of light and magnetism seems to follow clear rules, but what happens when we push our understanding to the very smallest scales, where light itself reveals a deeply paradoxical nature? The quantum world shatters our everyday intuition. A single photon of light can be in two places at once, a concept so strange even physicists struggle to grasp its meaning. This fundamental weirdness is perfectly captured by a deceptively simple experiment. Shine a light through two narrow, parallel slits onto a screen. If light were purely a wave, like a ripple on a pond, it would pass through both slits and create an interference pattern of bright and dark bands on the screen, which is exactly what we see. But here is the mystery. If you slow the light down and send just one single photon at a time toward the slits, each photon still builds up that same interference pattern over time. It is as if each individual particle of light passes through both slits simultaneously and interferes with itself. This is the wave-particle duality in action, a core principle of quantum mechanics where light is both a localized particle and a spread-out wave, its nature defined by how we choose to observe it. This bizarre behavior has deep roots. Albert Einstein first introduced the concept of the photon to solve the puzzle of the photoelectric effect. He realized that light could not simply be a continuous wave to explain why shining light on a metal could eject electrons. Instead, it must deliver its energy in discrete packets or quanta, which we now call photons. Each photon's energy is tied directly to its color, with blue photons packing more punch than red ones. This particle-like explanation, which earned Einstein his Nobel Prize, seemed to contradict the wave-like evidence from the double-slit experiment. The universe was speaking in two different languages, and both were correct. Decades later, physicists developed a complete theory to describe this dance. Quantum electrodynamics, or QED, paints a picture where photons are the carriers of the electromagnetic force, constantly exchanged in the interactions between light and matter. The legendary physicist Richard Feynman called it the jewel of physics, noting that its predictions are so precise they are like calculating the distance from New York to Los Angeles to within the width of a single human hair. But QED's implications are even stranger, leading to phenomena like quantum entanglement. Two photons can be created together in such a way that their properties become inextricably linked. Measuring the polarization of one photon instantly determines the polarization of the other, no matter how far apart they are in the universe. This spooky action at a distance, as Einstein termed it, has been confirmed through tests of Bell's inequalities, proving that the quantum connection is real and that our classical notions of locality are profoundly incomplete. These are not just laboratory curiosities. The highest energy light in the cosmos, gamma-ray photons from distant blazars, can exhibit quantum effects as they journey across the universe. On their way to us, these powerful photons may spontaneously transform into hypothetical action particles and back again in the presence of intergalactic magnetic fields, a quantum oscillation that changes the very light we expect to see. This quantum essence also powers the technology we use to explore the cosmos. The laser, a device that produces a coherent beam of light where all the photons march in lockstep, relies entirely on quantum principles. We use lasers for everything from measuring the precise distance to the moon to the search for gravitational waves with observatories like LIGO. As we grasp light's quantum nature, we inevitably run into its ultimate limits. The finite speed of light creates a horizon around us, a sphere beyond which we cannot see because the photons have not had time to reach us since the beginning of the universe. The quantum weirdness that defines light's behavior may even play a role in the fabric of spacetime itself, with some theories suggesting that the smooth continuum we perceive is an emergent property of countless entangled photons. We are left peering into the darkness, wondering if the final secrets of the cosmos are written not in the light we can see, but in the quantum shadows it casts. Our cosmic vision has a final, unbreakable boundary. We call it the particle horizon, the absolute edge of everything we can ever possibly see. This is not a physical wall in space, but a wall in time. It marks the distance that light has been able to travel in the 13.8 billion years since the universe began. The most distant photons that can reach our telescopes set this ultimate limit. The truly staggering part is that the radius of this observable sphere is not 13.8 billion light-years, because the universe has been expanding during the entire journey of that ancient light. The most distant objects we see are now actually about 46.5 billion light-years away. Beyond this particle horizon lies a cosmos we cannot access, realms from which no light, no signal, no message has had time to reach us. They are forever beyond our view. This is profoundly different from another kind of cosmic boundary, the event horizon. While the particle horizon is about what we can see from our past, the event horizon is about what we can influence in our future. Due to the universe's accelerating expansion, there are distant galaxies whose light we see today, but any signal we send now will never reach them. They are passing beyond our cosmic event horizon, receding into a future of permanent isolation. Then there is the Hubble sphere, the distance at which galaxies appear to recede from us at the speed of light. This is not a true horizon, but it highlights how the stretching of space itself defines our limits. The theory of cosmic inflation, championed by physicists like Alan Guth, suggests a mind-bending reality. Guth proposed that the entire universe we can observe is just a tiny patch within a vastly larger, perhaps infinite, whole. The rapid inflationary expansion in the first fraction of a second would have pushed other regions far beyond our particle horizon. These unobservable domains could have entirely different properties, even different fundamental constants of physics. Some theories suggest our universe might be just one bubble in a frothing cosmic foam of infinite bubble universes. We are forever confined to our own bubble, able to theorize about the others but never to observe them. So what lies in that eternal darkness beyond our sight? Are there alternate realities with different histories, or cosmic structures so alien we cannot even conceive of them? The light that defines our horizon also points to a future where it becomes more than a messenger. The same photons that carried the story of creation could one day be harnessed as a literal energy source, powering humanity's journey to the stars. Light, our oldest guide, may ultimately become the fuel for our final frontier. That gentle pressure you feel from sunlight on your skin is the very force that could one day carry us to the stars. It is called radiation pressure, and it proves that light, despite having no mass, carries a real and tangible momentum. Each photon that strikes a surface gives it a minuscule push. For our daily lives, this push is undetectable, but in the vacuum of space, without friction or gravity to fight, this tiny force can accumulate into a powerful and continuous acceleration. The concept is simple yet profound. A spacecraft unfurls a vast, ultra-thin, and highly reflective sail. Photons from the sun or from a powerful Earth-based laser bounce off this mirror-like surface, transferring their momentum and pushing the sail forward. It is a vessel with no engine and no fuel, riding on light itself. The visionary Carl Sagan often spoke of this, imagining it as the technology that would finally allow humanity to become an interstellar species, to reach out and touch the stars not in generations but within a human lifetime. This dream is now being tested. Japan's Ikaro's mission was the first to successfully demonstrate solar sail technology in interplanetary space, proving that a spacecraft could indeed be propelled and controlled by the gentle pressure of sunlight alone. But for journeys between stars, sunlight is too weak. The ambitious Breakthrough Starshot project envisions a different path, one that relies on a different kind of light. The plan is to construct a vast array of ground-based lasers, combining their beams into a single, colossal light cannon. This concentrated beam would target a tiny, gram-weight probe attached to a light sail no bigger than a picnic blanket. For a few minutes, this photon blast would accelerate the tiny craft to an unimaginable speed, 20% the speed of light. At that velocity, a flyby of Proxima Centauri, our nearest stellar neighbor, would take just over 20 years. How might this change our place in the cosmos? It transforms interstellar travel from a multi-generational epic into a mission that could return data within a single human career. We could send fleets of these tiny messengers to dozens of nearby stars, becoming true explorers of our galactic neighborhood. This is not science fiction, but engineering on the horizon, a direct application of the oldest force in the universe. The very same photons that ignited the first stars and carved the galaxies are now being harnessed as a gentle wind to carry our curiosity across the deep. The cosmic dark ages ended in a blaze of ultraviolet fire. After hundreds of millions of years of silence, the first stars and galaxies ignited, and their brilliant light began a second great transformation of the cosmos. This was the era of reionization, a universal upheaval where the very nature of space was changed once more. The intense ultraviolet radiation pouring from these first stellar furnaces was so powerful it blasted through the vast clouds of neutral hydrogen gas that filled the universe. This radiation ripped electrons away from their atoms, reionizing the gas and permanently clearing the cosmic fog for certain energies of light. The universe, which had become transparent once to the cosmic microwave background, was now made transparent to the higher energy light of stars and galaxies. This epoch unfolded between roughly 150 million and 1 billion years after the Big Bang, and we can still read its history today. One of the clearest signatures is found in the light of the most distant quasars. As that light travels for billions of years to reach us, it passes through immense clouds of intergalactic hydrogen. If that hydrogen is neutral, it greedily absorbs specific wavelengths of the quasar's light, creating a stark, dark band in the spectrum known as the Gunn-Peterson trough. The absence of this trough in the light from nearer quasars tells us that by about 1 billion years after the Big Bang, the hydrogen had been mostly reionized, the cosmic dawn was complete. We see another clue imprinted in the oldest light of all, the cosmic microwave background. The scattering of photons by electrons during reionization leaves a distinct mark on the polarization of this background radiation. By measuring this polarization with satellites like Planck, we can estimate when reionization occurred and how long it lasted. But what were the cosmic engines that powered this great transition? Astronomers like Jane Rigby use powerful tools like the James Webb Space Telescope to look back to this formative era. They are finding that early galaxies, smaller and more abundant than previously thought, likely provided the relentless ultraviolet radiation needed to carve these transparent bubbles in the fog. Supercomputer simulations show these bubbles growing and overlapping over hundreds of millions of years, eventually filling the entire universe with ionized gas. This was not a gentle sunrise, but a chaotic, patchy process that fundamentally shaped the future of cosmic structure. The end of reionization set the stage for the universe we recognize, a clear and structured expanse where light could travel almost unimpeded. It was this newly transparent cosmos that allowed the intricate patterns of galaxies to emerge and evolve. and it is within this clear, starlit universe that we now turn our gaze to an even more profound question, using light's signature to search for the ultimate cosmic discovery. The light from a distant star holds more than just the story of its own birth. As it filters through the atmosphere of a faraway world, it becomes a chemical sampler, picking up the faintest fingerprints of alien air. Astronomers catch this subtly altered starlight and stretch it into a spectrum, searching for the specific dark lines that betray the presence of water vapor, methane, or oxygen. This technique, called transmission spectroscopy, turns a planet's atmosphere into a revealed document, and its most sought-after entries are known as biosignatures. These are gases or combinations of gases that, if found, could suggest the presence of life. Oxygen is a powerful example. In our own atmosphere, oxygen is constantly replenished by photosynthesis. Without life, it would quickly vanish, binding with rocks and vanishing from the air. Finding significant oxygen on a temperate, rocky exoplanet would therefore be a monumental clue. But scientists are cautious. A biosignature is not proof, it is a compelling hint. A planet might have geological processes that mimic biology, producing methane without any need for life. The true goal is to find a chemical imbalance, an atmosphere that is stubbornly out of equilibrium, much like Earth's own mix of oxygen and methane, which constantly react and would neutralize each other if not for living things continuously pumping both into the air. Missions like Kepler and TESS have been our scouts, discovering thousands of these alien worlds and identifying the most promising targets. They found entire systems of planets, like the 7 rocky worlds orbiting the faint star TRAPPIST-1, several of which orbit in the temperate zone where liquid water could exist. But it is the James Webb Space Telescope that is transforming the hunt. With its immense mirror tuned to the infrared, it can dissect the light from these tiny, faint worlds, looking for the spectral signals of water, carbon dioxide, and perhaps even the telltale signature of ozone, a molecule that often partners with oxygen. Astrobiologist Sarah Seeger speaks of this as a new golden age, where we are no longer just finding planets, but are beginning to interrogate them, to ask what their air is made of. The ultimate dream is to see a planet directly. Future missions, concept telescopes with giant starshades to block the blinding glare of a parent star, aim to capture the pale blue dot of an exoplanet and analyze its reflected light. What colors would we see? Would the spectrum show the distinctive red edge of vegetation or some other utterly unfamiliar pigment? To find such light-based evidence of life would redefine our place in the cosmos. It would mean that the same physics that lets a leaf scatter green light on Earth might be at work beneath an alien sun. Light is the universal messenger, and its language of spectra and colors appears to be a constant across the universe. But is it truly the same everywhere? Could the fundamental nature of light itself hold one final, profound secret? The speed of light is the universe's ultimate speed limit, a cosmic rule so fundamental it seems written in stone. We learn it as 299,792 kilometers per second, a constant symbolized by the letter C that anchors Einstein's theory of relativity. But what if this rule was not always a rule? The first person to realize light had a measurable speed at all was the Danish astronomer Ole Romer. In the 1670s, he was studying the moons of Jupiter, timing how they disappeared behind the giant planet. He noticed something strange. The eclipses happened later than predicted when Earth was farther from Jupiter in its orbit, and earlier when Earth was closer. The only explanation was that light took time to travel across the vast expanse of space. His calculation was rough, but the principle was revolutionary. Light did not arrive instantaneously. It had a finite speed, Centuries of refinement followed, from laboratory experiments with spinning gears to modern laser interferometry that pins the value down with breathtaking precision. This constancy is the bedrock of modern physics, yet a handful of physicists dare to ask a heretical question: what if the speed of light was not always constant? Cosmologist Joe Megiddo has proposed a radical alternative known as variable speed of light cosmology, or VSL. He suggests that in the universe's first, unimaginably hot moments, light traveled much, much faster. This is not a minor adjustment, it is a fundamental rethinking of cosmic dawn. Why propose such a thing? Because our standard model of the universe, the Big Bang with inflation, has some persistent puzzles. One is called the horizon problem. When we look at the cosmic microwave background, the oldest light in the universe, we see that it is almost perfectly uniform in temperature. The problem is that regions on opposite sides of the sky were too far apart for light or heat to have ever traveled between them, not in the time available since the Big Bang. How did they reach the same temperature if they were never in contact? The prevailing theory of cosmic inflation solves this by proposing a period of faster-than-light expansion, stretching a tiny, uniform patch into our entire cosmos. But Megiddo and others offer a different solution. If light itself traveled faster in the early universe, then distant regions could have communicated and equalized their temperature before the speed of light settled down to its current value. This variable constant could be the key to a deeper law, one where the fundamental rules of physics themselves evolve as the cosmos cools and expands. It forces us to ponder a profound possibility. Are the laws of nature truly fixed, or are they more like cosmic habits, patterns that emerged and solidified as the universe aged? The light arriving from a distant quasar carries its ancient message, a spectrum shifted by the expansion of space. But if the constants that govern that light were different when it began its journey, the very meaning of its message could change. This is not just about speed, it is about the integrity of every photon as an information carrier across the entire electromagnetic spectrum, from radio waves to gamma rays. The constancy of light is what allows us to trust the cosmic story it tells. To question that constancy is to wonder if we are reading the universe's diary correctly, or if we have missed a footnote explaining that the alphabet itself has changed. Our eyes perceive only a sliver of the universe's true radiance. That beautiful rainbow from red to violet is a tiny window in a vast cathedral of invisible light, a full spectrum of energy from the long, gentle rolls of radio waves to the furious, staccato bursts of gamma rays. Each type of light carries its own unique story, revealing cosmic phenomena our biological vision is blind to. To see the universe in its entirety, we had to build eyes for all these different colors. Giant radio telescopes like the Atacama Large Millimeter Array, or ALMA, tune into the long wavelength whispers of cold gas and dust. They peer into the stellar nurseries where stars and planets are currently coalescing from frigid, dark clouds, listening to the faint emissions of molecules that will one day become part of new solar systems. In the infrared, telescopes like the Spitzer Space Telescope feel the warmth of the cosmos. Because infrared light slips easily through obscuring dust, Spitzer could see the glowing hearts of dense clouds, spotting newborn stars still wrapped in their dusty blankets long before they were visible in ordinary light. Then there are the high-energy realms. X-ray telescopes such as the Chandra Observatory see the universe in its most violent and energetic states. They reveal the superheated gas, millions of degrees hot, swirling at the precipice of a black hole, or the furious shockwaves from exploded stars. The pioneer of this field, Riccardo Giacconi, had to fight to prove this invisible light was worth studying. He launched the first X-ray telescope, and was stunned to find the sky ablaze with high-energy sources, from binary stars cannibalizing each other to the brilliant, pinpoint hearts of distant galaxies. His work opened an entirely new window on the cosmos, proving that to understand the universe, you cannot just look at it. You have to feel its heat and listen to its faintest radio songs. The difference between these types of light is simply their energy. A radio photon is lazy and low energy, while an X-ray photon is a tightly wound spring of power, born from the most extreme events in nature. This multi-wavelength vision transforms our view of familiar places. The center of our own Milky Way galaxy is completely hidden from our eyes by thick lanes of dust. But in infrared light, the curtain is pulled back, revealing a dense, bustling downtown of stars. In radio waves, we can trace the fierce magnetic fields and even pinpoint the location of the supermassive black hole, Sagittarius, a star lurking silently at the very core. By combining these views, we get a complete cosmic picture, a three-dimensional understanding that any single wavelength could never provide. This expanded vision allows us to trace the flow of energy from the birth of a star in an infrared cloud to its eventual death in an X-ray supernova remnant. Having mapped the universe across all its radiant energies, we are left with a deeper puzzle. How did this entire magnificent structure, with its galaxies and voids and cosmic web, get its start? The answer may lie in a fleeting, explosive moment at the very dawn of time. The universe's first moments were not a gentle expansion, but a violent, exponential growth spurt. In a fraction of a second smaller than any we can easily comprehend, the fabric of reality itself ballooned from a subatomic speck to a volume larger than our entire observable universe. This is the theory of cosmic inflation, a breathtaking idea that solves profound mysteries about the cosmos we see today. Why is the universe so uniform? The cosmic microwave background shows a nearly perfect temperature across the entire sky, yet regions on opposite sides were once too far apart for light to have connected them. Inflation solves this horizon problem by proposing that the entire observable universe was once a tiny, uniform patch that was stretched to cosmic proportions faster than light could cross it. It also explains the universe's surprising flatness, its lack of severe curvature, because inflation would have stretched space-time so much that any initial curvature would be smoothed out to near perfection, like blowing up a tiny, wrinkled balloon to the size of the Earth. The driving force behind this explosive event was a hypothetical energy field called the inflaton. As this field decayed from its high-energy state, it released a tremendous burst of energy that reheated the universe, filling it with the hot plasma of particles and radiation that would eventually form the cosmic microwave background. But inflation did more than just smooth and flatten the cosmos. It also planted the seeds for all future structure. Microscopic quantum fluctuations, tiny ripples in the energy field, were stretched to astronomical sizes by the inflationary expansion. These became the primordial density fluctuations, the slight over-densities and under-densities in the early plasma that gravity would later amplify into the vast cosmic web of galaxies and voids. We see the imprint of these seeds directly in the minute temperature variations of the cosmic microwave background. Yet the most sought-after evidence for inflation is even more subtle, etched not in temperature but in the very twist of ancient light. As the universe inflated, it is believed to have generated powerful gravitational waves, ripples in the fabric of spacetime itself. These waves would have left a distinct, curling pattern in the polarization of the cosmic microwave background, a specific signature known as B-mode polarization. Finding this pattern would be like hearing the echo of creation's first shudder. The search for this signal is one of the most challenging in modern cosmology. In 2014, the BICEP-2 experiment made headlines with an announcement that they had detected this primordial B-mode signal. The excitement was palpable, a potential direct glimpse into the inflationary era. However, further analysis in collaboration with the Planck satellite revealed that the signal was largely, if not entirely, caused by interstellar dust within our own Milky Way galaxy. This episode underscores the immense difficulty of this hunt, a reminder that the oldest light carries many overlapping stories. The implications of inflation stretch the imagination beyond our single universe. Physicist Alan Guth, who first proposed the theory, and others like Andre Linde, who developed it, suggest that once started, inflation may be eternal. In this view, our entire cosmos is just one bubble in a frothing, infinite multiverse, with other bubble universes constantly popping into existence, each with potentially different physical laws. As Linde has pondered, we may be living in a cosmic archipelago where the nature of reality is different on distant shores. This brings us to the ultimate question of origins. What set off inflation? What existed before the Big Bang? Inflation pushes our inquiries to the very limits of physics, suggesting that the universe may have arisen from a random quantum fluctuation in a deeper, more fundamental nothingness. The light from the cosmic microwave background is our only time capsule from that primordial era, and its polarized whispers are our best hope for understanding how everything began. If light itself can carry the scars of spacetime's violent birth, then perhaps the photon is not just a traveler through the cosmos, but an intrinsic thread in its very fabric. A beam of light does not always travel in a straight line. During the total solar eclipse of 1919, astronomers confirmed a staggering prediction. Stars near the obscured sun appeared slightly out of place, their light subtly bent by the sun's immense gravity. This was the first direct proof of Albert Einstein's general theory of relativity, which proposed that massive objects warp the very fabric of spacetime. Light, always following the straightest path through this curved geometry, must curve along with it. Einstein himself described light as having a dual role, a probe that both defines and is defined by the structure of reality. This warping of spacetime has profound consequences for time itself. According to his special theory of relativity, the faster you move through space, the slower you move through time. This is time dilation. A clock on a fast-moving GPS satellite, for instance, literally ticks slower than an identical clock on the ground. Furthermore, the satellite, high above Earth, experiences less gravitational pull, and since gravity also slows time, its clock ticks faster from that effect. The satellite's speed and its position in Earth's gravity will create competing time distortions that must be corrected by its onboard computers. If they were not, the GPS in your phone would accumulate errors of several miles within a single day. This is not a theoretical abstraction. It is engineering we rely on every time we navigate. This gravitational time stretching also creates a phenomenon called gravitational redshift. As light struggles to climb out of a powerful gravity well, it loses energy and its wavelength stretches, shifting toward the red end of the spectrum. This effect finds its ultimate expression at the edge of a black hole. The event horizon is the point of no return, the boundary where the gravitational pull is so intense that the escape velocity equals the speed of light. Nothing, not even light itself, can break free. This is why black holes are invisible, perfect cosmic voids. Yet we can detect them because their colossal warping of spacetime acts as a powerful gravitational lens, bending and distorting the light from stars and galaxies behind them, revealing their presence through this ghostly distortion. This interplay of light and gravity forces us to reconsider the very nature of cosmic distance and age. When we look at a galaxy a billion light-years away, we are seeing it as it was a billion years ago. But that simple statement hides a deeper truth. The space between us and that galaxy has been stretching during the entire journey of its light. The galaxy is now much farther away than the distance its light traveled. The age we measure for the universe, its expansion history, even the existence of dark matter, all are interpreted through the unbreakable rules that light and relativity have laid down. Could it be that this same light, by tracing the gravitational influence of the unseen, will finally illuminate the true nature of dark matter itself? An entire galaxy can spin so fast it should tear itself to pieces, yet it holds together perfectly. This cosmic contradiction is the work of an invisible hand, a substance that does not glow, absorb, or reflect a single photon of light. We call it dark matter, and its existence is written entirely in the behavior of the light we can see. Astronomer Vera Rubin's meticulous work on galaxy rotation curves revealed the problem. The stars at the outer edges of spiral galaxies were moving far too quickly. If the only gravity came from the visible stars and gas, these galaxies should have flown apart long ago. The only explanation was a massive, unseen halo of something holding everything together with its gravitational pull. Light from those distant stars told us what our eyes could not see, that most of the matter in the universe is completely invisible. We can even witness a dramatic collision between this dark stuff and ordinary matter. The bullet cluster provides a stunning case. It is actually two galaxy clusters that have smashed right through each other. The hot X-ray emitting gas, which is most of the normal matter, was slowed and tangled in the collision, but maps created by measuring how the cluster's gravity bends background light, a technique called gravitational lensing, show that the bulk of the mass, the dark matter, sailed right through the crash unscathed. It is a direct image of dark matter separated from normal matter, its presence outlined purely by the way it distorts the light from galaxies behind it. This shadowy component is not a small amount. The subtle patterns in the cosmic microwave background, the oldest light, confirm that dark matter makes up about 25% of the universe, while the stars, planets, and gas we see constitute less than 5%. So what is this elusive substance? Physicists have proposed candidates like WIMP, or weakly interacting massive particles. These hypothetical heavy particles would rarely interact with normal matter except through gravity. Another candidate is the action, an incredibly light particle that, under strong magnetic fields, might occasionally convert into a photon of microwave light. This gives experimenters a way to hunt for it, deep underground, in abandoned mines shielded from cosmic rays. Detectors wait for the faint flash of light or burst of heat that would signal a WIMP colliding with an atom. Other experiments use vast vats of liquid xenon, hoping to see the telltale scintillation of a single, rare interaction. We are essentially building traps to catch a ghost, using light itself as the snare. Could dark matter interact with light in ways we have not yet imagined, perhaps through subtle distortions we are only now learning to measure? This invisible architecture guides the formation of every galaxy and dictates the large-scale structure of the cosmos. It is the hidden skeleton upon which the visible universe is built, and its discovery through the bending and behavior of light marks one of the most profound triumphs of scientific inference. From this shadowy realm of matter that reveals itself only through gravity, we find our perspective shifting. The same light that exposes the universe's deepest physical secrets has also, throughout human history, shaped our most fundamental ideas about reality itself. Ancient Egyptians saw the sun god Ra sailing his bark across the sky, a divine mystery that demanded worship. For most of human history, light was synonymous with the sacred, a life-giving force beyond human comprehension. The Greek titan Prometheus was punished for eternity for stealing fire from the gods and gifting it to humanity, a myth that captures the awesome power we attributed to illumination. This reverence slowly transformed into inquiry. In the Arab world, scholars like Ibn al-Haytham conducted rigorous experiments in optics, correctly proposing that vision occurred when light reflected off objects and entered the eye, challenging earlier theories of rays emanating from the eye itself. The real turning point arrived with a simple prism in Isaac Newton's Cambridge room. He darkened the room, allowed a single beam of sunlight to enter, and watched it fracture into a brilliant spectrum on the far wall. This was not magic, it was a physical property of light itself. Newton had proven that white light was a mixture of all colors, a fundamental truth hidden in plain sight. This shift from divine symbol to measurable phenomenon accelerated rapidly. Centuries later, James Clerk Maxwell wrote down a set of elegant equations that unified electricity and magnetism, predicting that these combined forces traveled in waves at a specific, staggering speed, the speed of light. He had uncovered light's true identity as an electromagnetic wave. This scientific understanding did not diminish light's power to inspire, it amplified it. Leonardo da Vinci called light the most noble of natural phenomena, the painter's primary tool for revealing form and emotion. The practical application of this knowledge reshaped our world. The grinding of lenses, once an art for creating spectacles, gave us the telescope. Galileo's refinement of the spyglass turned it toward the heavens, revealing mountains on the moon and moons around Jupiter, forever changing our cosmic address. The same principles, applied in reverse, created the microscope, unveiling a bustling, unseen universe in a drop of water. Our entire modern world, from fiber optic cables transmitting global conversations to laser surgery and solar power, is built upon this centuries-long conversation with light. We began by worshipping the sun and ended up harnessing its very essence, our relationship with illumination forever marking our journey from myth to measurement. This historical foundation now propels us toward a future where light may reveal realities even stranger than any myth. 30-meter mirrors are rising from mountaintops, engineered to catch starlight with a clarity once thought impossible. These are the extremely large telescopes, instruments so vast they will gather more light than all the great historical telescopes combined. Their primary mirrors, segmented into hundreds of hexagonal pieces, will float on a thin film of air, their shapes continuously adjusted by thousands of actuators to maintain perfect form. This is not merely a larger eye on the sky, it is a new kind of vision. With this colossal light-gathering power, astronomers will not just see distant exoplanets, they will analyze their atmospheres in search of biosignatures, and they will watch the weather on worlds orbiting other stars. The European Southern Observatory's own ELT, under construction in Chile's Atacama Desert, will use its 39-meter mirror to study the atmospheric composition of rocky planets within habitable zones, perhaps finding the first chemical hints of life beyond Earth. Alongside these terrestrial giants, a new generation of space observatories prepares for launch. The James Webb Space Telescope is already peering into the infrared, its gold-plated beryllium mirrors tuned to see the heat glow of the first galaxies as they ignited. It sees in a light our eyes cannot perceive, a light stretched by the universe's expansion from visible ultraviolet into the infrared, the color of cosmic dawn. But light is not the only messenger. The Laser Interferometer Space Antenna, or LISA, will listen for the ripples in spacetime itself. This formation of three spacecraft, flying millions of kilometers apart in a perfect triangle, will use laser beams to measure the infinitesimal stretching of space caused by passing gravitational waves. It will hear the mergers of supermassive black holes and the faint rumble from the universe's earliest moments, a completely new sense with which to explore the cosmos. To see clearly from the ground, astronomers must peer through our shimmering atmosphere. The solution is adaptive optics, a brilliant technological dance. A powerful laser is fired into the sky, creating an artificial guide star by making a layer of sodium atoms in the upper atmosphere glow. Sensors then measure how this fake star's light is distorted, and a deformable mirror in the telescope changes its shape hundreds of times per second to cancel out the blurring. The result is a view from the ground that rivals the clarity of space, revealing details in galaxies once lost to the atmospheric haze. These tools will also conduct immense spectroscopic surveys, capturing the light of tens of millions of galaxies. By measuring their redshifts with exquisite precision, we will create a three-dimensional map of the cosmos on a scale never before attempted. As project scientist Gunther Hasinger has stated, this map will allow us to trace the subtle effects of dark energy across billions of years, watching how its repulsive force has altered the expansion rate of the universe over cosmic time. We will test the theory of inflation by looking for its unique signature in the arrangement of galaxies, a pattern imprinted from the primordial universe. What new mysteries will this river of photons unveil? We might find that the first stars were not alone, but existed in vast, chaotic clusters. We could witness the real-time weather on a gas giant exoplanet, or hear the gravitational wave background from the birth of spacetime. This enhanced light collection does more than answer old questions. It reveals new puzzles we have not yet learned to ask. As we look ahead, we see that light will continue to be our guide, not just to the universe's past, but to the very edge of its ultimate fate, a story still being written in every photon that journeys across the dark. The legacy of light is a story with an inevitable final chapter, written by the silent, relentless force of dark energy. In a future so distant it defies comprehension, the very expansion of space that allows us to see the deep past will ultimately sever our connection to the cosmos. As the universe continues to accelerate, the light from distant galaxies will be stretched beyond the point of recognition, their photons redshifted into utter oblivion. Over trillions of years, the brilliant tapestry of the night sky will slowly unravel. One by one, the galaxies will blink out, not because they have died, but because their light can no longer reach us. The space between our galactic neighborhood and all others will be stretching faster than light itself can traverse it, creating an insurmountable horizon. Cosmologist Lawrence Krauss has starkly described this as the end of astronomy, a time when all evidence for an expanding universe and a cosmic beginning will have vanished beyond our observational reach. In a mere 100 billion years, the view from our Milky Way will be profoundly lonely. The only visible objects will be the aging stars of our own local group, a small galactic cluster gravitationally bound to us. Every other island universe, every quasar and spiral nebula we catalogue today, will have receded into a permanent and absolute darkness. For any civilization arising in that far future, the cosmos will appear as a static island universe. They will have no way of knowing that a vast, dynamic cosmos once teemed beyond their sight, no cosmic microwave background to hint at a fiery birth. The entire epic history of light, from the first photon to the grand tapestry of galaxies, will be lost to them. This ultimate fate, known as the Big Freeze, is not a dramatic explosion but a slow, cold fading. Stars will burn out, new ones will cease to form, and space will continue to cool toward absolute zero. The photons that once carried the universe's story will have dissipated into a feeble, undetectable whisper. This cosmic ending forces a profound reflection. Our existence coincides with a precious, transient window in cosmic time, a unique era when the universe is both old enough for life to evolve and young enough for its ancient light to still be visible. We are living in the golden age of cosmic discovery, able to read the history of everything in the light that fills the void. What does this mean for our quest to understand? It imbues our search with a deep urgency and a poignant beauty. We are the universe's way of comprehending its own glorious, fleeting story before the final pages fade to black. The light we gather today is not just data, it is a message in a bottle cast across time, a legacy we must decode before the long night falls. The universe is expanding, but we do not know why. The force we call dark energy remains a ghost in the equations, a repulsive pressure accelerating the cosmos into a future of isolation. This is not the only gap in our understanding of light. Even the oldest picture we have, the cosmic microwave background, presents a profound puzzle. Its stunning uniformity is a mystery, for regions on opposite sides of the sky were once too far apart for light to have ever connected them. How did they reach the same temperature? The theory of cosmic inflation provides an answer, a period of faster-than-light expansion that smoothed the cosmos. But we are left asking what triggered that spectacular growth spurt and what powered it. We are now hunting for the faint, swirling fingerprints of primordial gravitational waves in the CMB's polarization, the last echo of that first violent shudder. Even the photon itself holds a secret. We assume it is massless, but what if it has an infinitesimally small weight? A massive photon would subtly alter the laws of electromagnetism over cosmic distances, and experiments are searching for this tiny deviation, a discovery that would rewrite fundamental physics. These are not abstract curiosities. The Hubble tension is a direct challenge to our cosmic models. Different methods of measuring the universe's current expansion rate yield conflicting results, as if the cosmos is giving us two different answers. Is our understanding of the early universe wrong, or is dark energy evolving in an unexpected way? The James Webb Space Telescope and next-generation CMB surveys like the Simons Observatory are now gathering data to resolve this crisis. They are measuring the light from the first stars and the subtle patterns in the ancient afterglow with unprecedented precision, hoping to find which path leads forward. Stephen Hawking once reflected that a complete theory of the universe should allow us to know the mind of a creator, and light, in its quantum weirdness and relativistic grace, is the central thread in that quest for a theory of everything. Each time we solve one mystery of light, we peel back a layer to find a deeper, more beautiful question waiting beneath. The journey that began with a single photon in the primordial dark continues, its final secret still traveling toward us, waiting in the light we have yet to see. Our journey through the hidden history of light reveals a cosmos deeply interconnected. From that first flash in the primordial fire to the faint microwave whisper that paints our entire sky, light has been the universe's constant narrator. It sculpted the first galaxies, exposed the invisible grip of dark matter, and delivered the startling news of an accelerating expansion. Every photon that lands in a telescope or glances off your eye is a time traveler, its color and path a chronicle of cosmic evolution, from stellar forges to the relentless stretch of spacetime itself. Carl Sagan's beautiful words ring true: the cosmos is within us. We are made of star stuff, and the very light that now illuminates our night sky is what forged those essential elements long ago. So tonight, find a moment to step outside and simply look up. Let your eyes adjust to the darkness, and as you gaze at those pinpricks of ancient fire, remember the epic journey each one has taken across billions of years to reach you. Consider that you are part of this grand story, a conscious moment in the universe looking back at itself. I would love to hear what wonders the night sky holds for you. Share your thoughts and reflections in the comments below, and if you enjoyed this journey, subscribe to continue exploring the profound mysteries of space.